Welcome everybody to Chapter 6, where we're going to be dealing with electrons and their electronic structure throughout here. First, we're going to have to go back and think about electrons and how they behave a little bit. And so we're going to start there, and then we'll move forward and actually get into those electronic structures. So first off is that, we're going to talk about the wave nature of light, and we've known about this for quite a while. And that the wave nature of light is that, light behaves as waves, and there are several defining characteristics to this that'll be helpful for us along the way. And number one is wavelength, which is given the symbol of lambda there. All right, and so wavelength is usually going to be given in either meters or nanometers, depending on what we're interested in. A lot of times things are going to be given in nanometers, but once we plug them into calculations, we're going to need them in meters. So I've given the conversion factor there. That 1 nanometer is equal to 1 times 10 to the minus 9th meters. And hopefully we can kind of remember that, right? That means that we have 1 nanometer per 1 times 10 to the minus 9th meters, or 1 times 10 to the minus 9th meters per 1 nanometer, depending on what the, way that we need to convert between there. The other thing is that we are going to be looking at frequency. Frequency says is a number of successive crests or troughs that pass through a point at a unit of time. And so really what that means is like how fast up and down our wave of light is moving. I like to think about this as like if you are sitting on a boat, right, rocking in the ocean or something like that, and you've got these waves coming by you, like how choppy is the water? Are you going up and down really slowly, or are you going up and down and up and down and up and down really, really quickly, right? Which way is that going to be? That is what we're talking about with frequency. Frequency is given in units of over time or over seconds, and that is also called hertz. So sometimes you might see this, like we've written it as 1 times 10 to the 8, right, per second, or, right, hertz means the exact same thing as per second does. It's just another way of calling the units. It's just another name for the same exact units, I guess. Okay, so we're going to do some quick calculations using frequency and wavelengths. So here it says that we've got the color orange, right? That's one of the ones that's within the visible light spectrum. We're going to talk about our different parts of the spectrum on our next slide. But it has a wavelength of around 620 nanometers. What is the frequency of orange light? Okay, well, there is a equation that we are going to use for this, where the speed of light is equal to wavelength times frequency, always. All right, and so if we keep that in mind, then we can do any of these. So what I'm going to do here is I'm just going to rearrange this, and I'm going to say, all right, I want to know the frequency, and so that is equal to the speed of light divided by our wavelength. All right, well, the speed of light, which is given the symbol of c, is 2.998 times 10 to the 8th meters per second. So our frequency is 2.998 times 10 to the 8th meters per second divided by our wavelength. Well, right? Notice that our speed of light has units of meters in it. So our wavelength also needs to have units of meters in it as well. So our wavelength of 620 nanometers, right? And we just saw on our previous slide there that we have 1 times 10 to the minus 9th meters per 1 nanometer. All right. And so this is going to be equal to 6.20 times 10 to the minus 7th meters. All right. So now we're cooking. We can just do our speed of light divided by that value, and we're going to end up with 4.8 times 10 to the 14th hertz, right? Or 4.8 times 10 to the 14th seconds to the minus 1. Both of those are acceptable. All right, another one here is light with a frequency of 7.26 times 10 to the 14th hertz is in the violet region. What is the wavelength of this frequency? All right, and it says that we want our answer in nanometers, so we can do that. Okay, so again, right, we want wavelength. So we've got C is equal to wavelength times frequency, or another way of writing that is wavelength is equal to C over frequency. So we've got 2.998 times 10 to the 8 meters per second divided by 7.26 times 10 to the 14th per second. And I promise you that these per seconds are going to cancel each other out. It's just the way that they are. Like the denominator of the denominator is in the numerator, and so they end up canceling out there. And so I'm going to get this value to be 4.13 times 10 to the minus 7th meters. All right, and again, we have 1 nanometer per 1 times 10 to the minus 9th meters. And so this is 413 nanometers. All right, so we can just kind of go back and forth between those things. All right, now when we look at this, right, we can look at what we call the electromagnetic spectrum. And here's showing the electromagnetic spectrum. And so there'll probably be some questions that have to deal with this. Again, right, I would have this on hand where it's really easy to kind of like navigate through. But notice that the visible light, right, when we talk about the electromagnetic spectrum, sometimes we just use this as a generic term for light is all of these things. But we usually think about light being like the visible light spectrum that we can see. And so if we look at the visible light spectrum, right, it is a very small area on this overall spectrum. There are also things like gamma rays and X-rays and radio waves and stuff like that, right? And what I want us to like note on here is look at the wavelengths, right? And then look at these frequencies, okay? And notice that the smaller the wavelength, the higher or bigger the frequency is. Okay, they are inversely related. Okay, that's something that we need to be able to kind of like think about, right? And we can see that if we know calculations that C is equal to the wavelength, right? As one of them goes up, the other one has to go down, right? Because they're both on the exact same side of the equal sign there. All right, now, not only does light behave as a wave, but we've also figured out that light behaves as a particle. All right, and this is a stream of particles that we sometimes call photons. All right, and so we figured this out by going back and running experiments, and those experiments from the early 1900s, like the 1900s to the 1910s, all right, showed that like if we shine light at very specific wavelengths and shine them onto like pieces of metal, we can actually get electrons to hop up out of that piece of metal. And so what that's telling us is that there has to be something that is actually striking that piece of metal, all right, and hopping those electrons off. And so then they also must have some sort of a particleness to them. And when we've got something that is a particle, it has to have some sort of energy associated to it. And we can calculate the energy of the particle of light as either saying that energy is equal to h nu, right? And h is Planck's constant, which is 6.626 times 10 to the minus 34th joules times seconds. All right. Nu is still frequency, right? Or E is equal to Planck's constant times the speed of light over the wavelength. All right. And I'm showing that all as one equation here. What I'm really doing though is I'm separating that. Those are two separate equations of how you can calculate energy. Either one of them will totally work, just dependent upon what information you're given. All right, so let's do a calculation then, right? So earlier, we were able to find that 620 nanometers, that was our orange light, was equal to 4.8 times 10 to the 14th hertz. Let's find the energy from these two values, all right? And I'm telling us that they should be identical to each other. So energy is equal to, let's start with h nu first. All right, so energy is equal to h, which is 6.626 times 10 to the minus 34th joules times seconds, times our frequency, 4.8 times 10 to the 14th, all right, per second. Look at that. We're going to be ending up with energy units of joules. Perfect. All right, and so we get this to be 3.2 times 10 to the minus 19th joules. All right, well, let's also do this with our wavelength. Energy is equal to hc over lambda. All right, so again, we have our h, 6.626 times 10 to the minus 34th joules times seconds. Our speed of light, we're going to plug that in, 2.998 times 10 to the 8th meters per second. All right, and we're going to divide by the wavelength, and that wavelength has to be in meters. So 620 nanometers is 6.20 times 10 to the minus 7 meters. I promise you that. You can go and do that calculation on your own just to double check it. Those meters cancel, and we get that this is 3.2 times 10 to the minus 19th joules. They are the exact same, so it doesn't matter which way we calculate it. If we start with nanometers or we start with the frequency, right, we can get the exact same answer. All right, our next topic is we're going to be looking at something that we call emission spectra. Okay, so when we've got elements in the gas phase, those elements in the gas phase, we can excite them by applying some sort of an external energy to them. All right, and when we do this, what we can do is we can excite electrons from one energy level to another. All right, and so we can excite these electrons from one energy level to another energy level, right, by putting energy in. And then when those electrons then relax or fall back down, right, they're going to give off a photon of light. All right, and that photon of light is going to have a very specific energy depending upon the level of which it falls down. So if I fell from, say, here down to here, right, this would have a very specific wavelength associated with it. Versus if I fell from here all the way down there, right, that's a very different amount of energy. that wavelength is going to be different, right? Because E is equal to hc over lambda, since the energy differences are different, then the lambda or the wavelengths are going to be different as well. Okay, now these photons are very specific depending upon the elements themselves. So if we look over here, we've got our emission spectra, right? If I've got something like hydrogen here, right, it's got a couple of emission spectra in the violet range there. It's got one in the blue and kind of one down there in the red area as well. Like it's got 4 in the visible area. Right, whereas like if you've got sodium, it's got a bunch of different ones. Right, it's got like a couple of them in the blue-green. It's got a couple in the, like 4 maybe in the yellow and one kind of in the orange range there. Right, and if you look at like a sodium lamp, like they look kind of yellow because that yellow dominates it. But this emission spectra is very dependent upon like those different energy levels that we have in the different elements themselves. All right, next up, we're going to talk about the development of quantum theory and the quantum numbers that are behind that. Okay, now we're not going to go really in depth on all of the different scientists who came along and put their thumbprints on this. We got plenty of that in the textbook. We got plenty of that in the more expanded PowerPoint slides that you can look over. You can look over, the Schrodinger equation and what it kind of solves for and everything like that. But what we want to get out of this is just like the basics for where the different quantum numbers that we're going to be interested in here come from and how we're going to use those to describe electrons in different orbitals. So first off, we need to describe what we call an atomic orbital. So it is a region of space, right, in which we are most likely to find a specific electron. Okay, it's where it's most probable to reside. It doesn't mean that it has to be right inside of there, but most likely, right, somewhere around 90 or 95% of the time, that is where that electron is going to be located. Right, and so we're going to give a certain like set of quantum numbers that'll tell us where that specific orbital is. Okay. The atomic orbital is not exactly an orbit. A lot of times you might think or have seen, you might have like a nucleus and then they might draw like some different like orbits around that nucleus where you might find electrons, and that's not really the case. What's really the case is that the orbitals where we actually find the electrons are these 3-dimensional spaces. Okay, so it's not just these nice little concentric rings that we think about like, like the planet orbiting around the sun. What they really are these 3-dimensional spaces, which were calculated by something called the Schrodinger equation. All right, and that is a very complicated equation that you can solve for if you want to move on to physical chemistry. But in here, we're just going to assume that it was calculated, and we're going to find a few different quantum numbers from that. Number one of the 3 different numbers that solves for it is the principal quantum number, all right, which we give the symbol of an N. And that basically is describing the size or the energy of our atomic orbital. All right, and so our principal quantum number N, right, has values of 1, 2, 3, 4, etc. So and so the larger the N, okay, the bigger the orbital and the more energy it has. All right, next up we have something that we call the angular momentum quantum number, which is given the symbol of an L. All right, and this describes the shape of our orbital. Right, and I'll get into the different letters, notations, and stuff like that on the next slide. But right, what we can have is like we could have something like a sphere. We could have like these 3-dimensional like kind of dumbbell looking shapes. And we can get even more and more complicated along with that. But those angular momentum things, they're describing the actual shape of the orbitals themselves. And then lastly, we have what we call the magnetic quantum number. And this is the orientation in space. So as I showed here, right, I might have one going up and down, I might have one going side to side, or I might have one kind of like going in and out of space there, right? And so those are given by this magnetic quantum number. Okay, so right, our principal quantum number right, it can have values of 1, 2, 3, and 4, so they have to be, right, so they're going to start with 1, then 2, then 3, and then 4, and so on. Next up, we've got our angular momentum quantum number, which is L. All right, so this is where they get a little bit complicated, but L can have values of 0 up to n minus 1. Okay, so let's look at this kind of. So if we have an n of 1, then L can be 0 up to an n minus 1, which is 1 minus 1, which is 0. So it can only really have a value of 0. All right. If you have an n of 2, then L could be 0 up to n minus 1. All right, so 2 minus 1 is 1. So it could be 0 or 1. All right, these have to be whole numbers as well. N of 3, so n minus 1 or 3 minus 1 is 2. So L could be 0, 1, or 2. N of 4, L could be 0, 1, 2, or 3. All right, now the other thing, totally confusing, and we'd like to do this because, you know, as chemistry professors, we want to mess with chemistry students. All right, an L of 0 is also sometimes called an S. An L of 1 is called a P. An L of 2 is called a D. And an L of 3 is called an F. All right. Next, we've got these magnetic quantum numbers, M sub L's. All right, so the M sub L's, they can go from a negative L to a positive L. So M sub L, if you have, say, an L of 1, all right, your M sub L's could be minus 1, 0, or positive 1. An M sub L for an L of, I don't know, 3. Could be minus 3, minus 2, minus 1, 0, plus 1, plus 2, or plus 3. All right, I know. They're confusing, but we'll get them down, especially as we see some of these things actually play out and we use them. I think that they'll make more sense. All right, and then lastly, one that's not derived from the Schrodinger equation, but is another quantum number, is the M sub S, which is the spin quantum number. And that can either be plus 1/2 or minus 1/2. And that's just saying whether an electron is spinning one direction, right, or whether it is spinning the opposite direction of that. So electrons can spin one of 2 different ways so that they can pair up. All right, because electrons are negatively charged, they don't really like each other, but they pair up. And the only way that they can pair up is if they have opposite spins of each other, because they give off an electronic waves that'll then allow them to kind of stay close to each other there. or a magnetic area there that'll allow them to be close enough that way. Okay, so we can now use these then to find electron configurations. Okay, so in order to find electron configurations, we're going to do that one of several different ways, and you can do this whatever way makes the most sense to you. The first one is like we can set up a table that kind of looks like this here, and we can just fill in from the lowest energy to the highest energy by filling in the number of electrons that are present in it. Okay, and so here, right, just I want to first off notice that if you're in one given principal quantum number, that the order of the L, right, or the angular momentum quantum numbers, S, P, D, and F, right? Remember those were 0, 1, 2, and 3 sometimes. But the order of those energies, right, go from S to P to D to F. So the S is the lowest energy, the P is a little bit higher, the D is a little bit higher, and then the F is the highest of those still. Right, electrons like to fill from the lowest energy to the highest energy as they go along. And so one way we can do this is, let's say that you had, I don't know, let's say we're going to do scandium. It is number 21 on the periodic table, which means it has 21 protons, which means that it also has 21 electrons. Okay, now we can fill that up. And what we're going to do is we're going to fill in these lines from the lowest energy to the highest energy, and each line is an orbital, and it holds a maximum of 2 electrons. Okay, so I'm going to put in 21 electrons here from the lowest to the highest. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. All right, now I've run out of electrons. Okay, and when we want to write out an electron configuration, we're going to write it from the bottom, working our way up. So we would say we have 1s, and we put in 2 electrons in there. And then I move up to the 2s, and I put in 2 electrons there. Right? And then the next place we went was a 2p. And notice that there are 6 electrons in there, so 2p6. Then the next higher one is 3s. There's 2 electrons in there. And then the 3p, there's 6 electrons there. And then the 4s, there's 2 electrons in there. And then the 3d, and there's 1 electron in it. That's an electron configuration. And so one way of doing that is just by filling in a table like this. Right? There's a few different ways that we're going to do these. We're going to go through them, but that's one of the ways that we can fill in electron configurations. Right? The next slide is basically saying, hey, all right, so right, the electron configuration tells us, right, that principal quantum shell, 1, 2, 3, etc. The letter designation, right, that is S, P, D, etc. And then that superscript, right? So we had those 1s2, 2s2, right? That's N, that is L, and then that superscript is the number of electrons that were in that orbital itself, right? So we did those. All right. Now another way of doing this is writing out something along these lines, right? So if you want to do that, that's good too. So s orbitals can hold 2 electrons. P orbitals, if we notice down here, have 3 lines, so they can hold 6 electrons. D orbitals, have 5 lines, so they can have 10 electrons, and so on. And so we can fill using this as kind of a guide as well. This is another way to do it. If you weren't to have, say, like that bottom energy diagram there, you could use the next one. If you know the order in which things, so 1 can only have, right, an L of 0, which is an S, right? 2 could have a 0, which is an S, or a 1, which is a P. 3 could have an S, a P, or a D, right? And so that's where those are coming from, and so on and so forth as they're written out. Okay, so what we could do is, again, we could do the electron configuration for something like, say, germanium. All right, so germanium on the periodic table has 31 electrons. Okay, so here, in order to use the top one, I would write in, it's got a 1s. We go through it, it can hold 2 electrons. So I'm down to 29. All right, I keep following along. We went through that one. Next up, I get to the 2s. It can hold 2 electrons. So I'm going to mark that out. We're down to 27. I keep going. Next thing I get to is a 2p. Right, p's can hold 6. So 2p6. So 27 minus 6 is 21. We are going to keep going. Next thing I get to is a 3s. It can hold 2. 21 minus 2, I'm down to 19 electrons I can put in. Kind of roll up here, we get to the 3p. P's can hold 6. 19 minus 6. Right. We are down to 13 electrons to put in. Next I get to the 4s. They can hold 2. So they're down to 11. All right, next up I get to the 3d. It can hold 10 electrons. I've got 11 to put in. I put in 10, so I'm down to only 1 more electron. That 3d is full. I get to the 4p, and I get 4p1. So there's an electron configuration by using that top way as well. All right, the last way that we can do this is by using the actual periodic table. All right, and so by using the actual periodic table, it's knowing, right, where our s orbitals p orbitals and d orbitals are. All right, so again, I mean, I could do something. I'm going to do something a little bit easier, but I could do oxygen. Right, and so we could find oxygen here on our periodic table, right? I'm putting a little X there, marking our oxygen. So oxygen has, all right, I'm going to kind of mark these things. So 1s1, 1s2. All right, then it has 2s, 1, 2. Then it comes over here, and it is a 2p, 1, 2, 3, 4. So the electron configuration is 1s2, 2s2, 2p4. All right, and we can use the periodic table there by knowing where we are on the periodic table. All right, and again, S's are always there, P's are always there, D's are always there, F's are on the very bottom, and being able to work through those. It's just whatever you feel comfortable with. Again, you can have, like, open resources, so use what you're best with going forward. All right, so we're going to write the electron configurations for the following elements. sodium, chromium, and krypton. All right, so sodium, chromium, and krypton. Okay, so sodium is number 11 on the periodic table. It has 11 electrons. All right, chromium is number 24. It's 24. And krypton is number 36. Okay, so depending on what you like to do, all right, I'm going to use this one just because it's like right here. So I'm going to go 1s2, 2s2. So we've used up 4, 2p6. All right, so that's 10. I'm going to get to 3s. And we only have one more to put in, so that's a 3s1. All right. Again, right, just you do these on your own. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4, and 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. All right, so make sure that you can get the same things that I got there, running through those as well. All right, now, right, we can also write these out, because that takes a lot of work to write out all of those things. Right, a lot of times we'll write these as abbreviated electron configurations as well. Right, and abbreviated electron configurations are basically going to show the same thing, but we're abbreviating them by showing that, okay, the only thing that we really needed there is everything after the noble gas configuration, all right, because everything up to that should remain the exact same, right? So I'm showing like lithium has the electron configuration of 1s2, 2s1. Okay, well, if we look at the previous noble gas on the periodic table, get a periodic table out. Can't really move around on my slides here, but the previous noble gas to that is helium. Helium has an electron configuration of 1s2. So lithium has the electron configuration, the same electron configuration as helium, and it has then a 2s1 electron in it, right? Or our sodium, which we just did on the previous slide, right? Well, it had that electron configuration there. Well, also look, neon has the electron configuration of 1s2, 2s2, 2p6. Okay, that electron configuration is exactly the same as that is. And so we can shorthand, we can shorthand our sodium to being that it's identical to neon, plus it has that 3s1 electron as well. All right, so if we went back to, the ones on our previous slide, right, we could have our chromium has the electron configuration the same as argon, plus a 4s2 and a 3d4. Or krypton, well, krypton is a noble gas. All right, so there's really no There's really no abbreviated configuration, so you really have to write the whole thing out. All right. Now, lastly, right, what about the electron configurations for ions? All right, remember, ions are where we either gain or lose electrons, right? So cations, right, is where we have lost electrons, and anions is where we've gained electrons. And so what we do for these is we're going to write out the electron configurations for them, and then we're going to see what happens when we either gain or lose an electron to it. So we're going to write out the parent electron, or the one that doesn't have a charge. Then we're going to write it out with the charge associated with it. So again, right, I've got sodium is 1s2, 2s2, 2p6, 3s1. All right, sodium has lost one electron. All right, and when we lose electrons, we're going to lose from the highest principal quantum number first. So the sodium cation has lost one electron, all right, and it lost that one electron out there. So it's become 1s2, 2s2, 2p6. All right, phosphorus, if it was a neutral phosphorus, is 1s2, 2s2, 2p6, 3s2, 3p3. So phosphorus with a 3 minus charge we're going to add 3 electrons there to that 3p. So we get 1s2, 2s2, 2p6, 3s2, 3p3 plus another 3 is 6. All right, and then lastly, I've got that aluminum 2 plus. All right, aluminum really likes to be 3 plus, but here we're going to do it as a 2 plus. All right, so aluminum, let's start with just good old aluminum first, has 1s2, 2s2, 2p6, 3s2, 3p1. So aluminum 2 plus is going to lose 2 electrons. So it's going to lose 1 electron there from the 3p, and it's got to lose 1 more from there. So it's going to become 1s2, 2s2, 2p6, 3s1. Right? It lost one of those s2, and it lost the 3p1. So it's lost 2 total, right, to become that electron configuration there. All right, we've made it through another chapter. Chapter 6 is in the books. We'll see you next time for Chapter 7.